In the 14th lecture, we will cover the categorical predictors. Previously, the regression model we discussed only have numeric independent variables. Now we will learn how to use categorical variables as predictors. A categorical variable can be defined as a factor or class variable whose values can be either numeric or string. The different categories of a factor or class variable are called levels. In R, the function factor may encode any vector to a factor variable. Similarly, the class statement in SAS sets the class variable. For example, the students from two classes, class 1 and 2, can be described by a variable whose value is 1 or 2. The values are numeric, but the numeric values 1 and 2 don't have any mathematical meaning, and the variable is actually a factor or class variable that has two levels. A dummy variable or an indicator variable is a numeric variable. It may directly be used to code a two-level factor or class variable. For example, variable gender has two levels, male and female. Then we may encode it using a dummy variable dm, which is 0 for female and 1 for male. Also, we may use the SAS statement like this to define the class variable. Here, we set the reference level as class 1. It tells us we use a dummy variable d whose value is 0 if the student is in class 1, and 1 if the student is in class 2. If a variable has more than two levels, then we need to define more than one dummy variable. For example, variable education has three levels, high school or below, undergraduate, and graduate. Then we may use two dummy variables, d1, which is 1 for undergraduate, and 0 for others, and d2, which is 1 for graduate and 0 for others, to code the variable education. Thus, we have 0, 0 for high school or below, 1, 0 for undergraduate, and 0, 1 for graduate. Typically, we should use L-1 dummy variables to code a variable with L levels, and there is always one level that we use as the reference level. For example, we do not encode the reference level, which is high school or below in the education variable, as a dummy variable. Previously, we already defined dm for male. Let's define another dummy variable, df, which is 0 for male and 1 for female. Then if we use both dummy variables in the model, then we will have perfect multicollinearity since df is 1 minus dm. Thus, to avoid the dummy variable trap, we should not encode the reference level. Now let's take a look at an example. The SAS dataset has 36 observations and 3 variables. 2018 salary in thousands, education in 3 levels, high school, undergraduate, and graduate, and gender, male and female. Both education and gender are set as class variables. Here, high school and female are set as reference levels. Notice we use the HPReg procedure to allow the class variables. Thus, we code variable education into graduate and undergraduate dummy variables, and code variable gender into male dummy variable, as discussed earlier. The model has a R-squared value of 0.9, meaning that two variables have explained 90% of the variance in the outcome salary. The regression results show that the model has 4 parameters. One is intercept, and the other 3 are dummy variables. The significance of intercept suggests that we have a positive salary even all dummy variables are in the reference level. The results indicate that females with high school diploma earn an estimated 28K salary. The estimated coefficient for the graduate dummy is 60, suggesting that the salary for people with a graduate degree will be 60K higher than those with a high school diploma, holding the gender as constant. Similarly, the estimated coefficient for the male dummy is 11, suggesting that male salary is estimated to be 11K higher than female salary, holding the education level constant. When we have continuous outcome and categorical independent variables, we may also use ANOVA tests to compare the group means. Now let's compare the regression with ANOVA test. In ANOVA, we don't code the predictors into dummy variables. Thus, we don't need to set the reference levels. The test checks the null hypothesis that all group means are equal and is able to find the group mean difference in one test instead of multiple comparisons. The following table shows the two-way ANOVA test results of the salary example. The variable gender has a F value of 12.9, which is the square of the t-value 3.59 gotten from the regression, suggesting both the regression and the ANOVA tests are the same for a two-level class variable. For class variables that have more than 2 levels, the results look different because ANOVA test combines all levels in one statistic, while the dummy variable used in regression only compares one specific level to the reference level. Thus, the F value for the variable education 143.5 is a combination of two dummy variables, undergraduate and graduate, in the regression model. Finally, there are no reference levels in ANOVA, while in regression the intercept represents the reference levels. Thus, we may use either the regression or the ANOVA tests when we have categorical variables as predictors. The choice of the tests may depend on the research question. The ANOVA test compares all levels of a categorical variable, and the regression uses the dummy variable that gives us the pair comparison between the specific level and the reference level. The linear regression model may contain higher order terms, such as the interaction term. Interaction occurs when the effect of one variable depends on the value of another variable. In the linear model, the interaction effects may be represented by the interaction term, which is the product of independent variables. Below, the circled term is a two-way interaction term. If the interaction term is significant, then it suggests that the effect of x1 depends on the value of x2, or the effect of x2 depends on the value of x1. It means 1 unit increase of x1 will increase the outcome b1 plus b3 multiply x2, holding x2 constant. Or 1 unit increase of x2 will increase the outcome b2 plus b3 multiply x1, holding x1 constant. We may have interactions among categorical variables, interactions among continuous variables, and interactions among categorical and continuous variables. Both the regression and the ANOVA tests may include the interaction effect. Let's check an example that may tell us how to interpret the interaction terms in a regression model. The first model is the linear regression without the interaction term. Here, DG is the graduate dummy, DU is the undergraduate dummy, and DM is the male dummy. The high school level in education and the female level in gender are the reference levels. All terms are significant as discussed earlier. From the model, we may estimate the salary for each level. For example, the average estimated salary of men with the graduate education is $98.97 thousand, as the sum of 27.86 from intercept plus 60 from graduate dummy plus 11.11 from male dummy. The coefficient of the male dummy term B3 tells us the estimated average salary difference between men and women, holding the education constant. Here, the salary difference is 11.11K, highly significant with a p-value of 0.0011. The second model is the linear regression including two interaction terms, dg multiply dm and du multiply dm. We may also estimate the salary based on the model with the interaction terms. For example, the average estimated salary of men with the graduate education is $105.5 thousand at the sum of 30.83 from intercept plus 50.5 from graduate dummy plus 5.17 from male dummy plus 19 from interaction of graduate and male. We should notice the same dummy terms have different meanings if the interaction terms are included. For example, in the second model, the coefficient of the dummy term estimates the salary difference between men and women when the education is the reference level, which is high school. Here, the estimated salary difference is 5.17K, no longer significant, with a p-value of 0.28. Also, the education dummy variables have similarly different meanings when the interaction terms are included. The interpretations of interaction terms are rather counterintuitive. We may not be able to test the research question based on their significances. For example, the table shows the first interaction term graduate male is significant at a p-value of 0.0077. How do we interpret this significance? Does this mean men with the graduate education have an average salary significantly higher than women with the high school education, or men with the graduate education have an average salary significantly higher than all other levels, or men with the graduate education have an average salary significantly higher than the overall average salary, or none of above? The answer is D, none of the above. We may try to understand the interaction term based on a metaphor. We have two workers, David and John, assembling machine parts. David can assemble 8 parts, and John can assemble 10 parts when they work separately. But when they work together, they can assemble 20 parts per day. Dummy interaction terms tell us whether the extra contributions, in this case 2 extra parts, are significant. In the salary example, the first interaction term suggests that men with the graduate education have an average extra salary increase of 19K, in addition to the increase from graduate dummy 50.5K and the male dummy 5.17K compared to the base levels women with the high school education. We may interpret the second interaction term in a similar way. Since in practice we are seldom interested in the extra contribution, the interaction terms may not be used alone to answer the research question. We may also run ANOVA tests with the interaction terms. The first model does not include the interaction, and the second model includes the interaction. In the second model, the factors education and gender have larger f-values due to the smaller mean squared error. The mean squared error is 86 in the first model and 66 in the second model. The interaction term is significant, suggesting there is a significant difference in the effect of the education level between man and woman, or significant difference in the effect of the gender for different education levels. The term may be directly used in the hypothesis testing. In the salary example, the null hypothesis could be no difference in the effect of the education level for man and woman. We will reject the null hypothesis since the interaction term has a p-value of 0.007. Thus, the interpretation of the interaction term in ANOVA test is very different from that in linear regression. The ANOVA test shows the combined effects of all levels in the categorical variables. For example, the first two terms, education and gender, are the main effect. The interaction term in ANOVA shows us the combined effects of all interaction levels on the salary. It is the interaction effect. Here, the interaction effect is much smaller than the main effect. Since the interaction effect is the combined effects of all levels, we may not know if all interaction levels have a similar effect. We may use the interaction plot to further explore the ANOVA results. For example, this is an interaction plot of the salary example. From the graph, we observe the lines between high school and undergraduate are almost parallel, and the lines between undergraduate and graduate are not parallel, suggesting significant interaction effect mostly exists in the graduate education level. In summary, we learned how to use and interpret the categorical variables as predictors. A categorical variable can be defined as a factor or a class variable, and thus code it using one or more dummy variables in a regression model. We may also use the ANOVA tests for the categorical predictors. The ANOVA test tests the combined effect of all levels of a categorical variable, and the regression test compares the specific level to the reference level. Interaction occurs when the effect of one variable depends on the value of another variable. We may use the interaction term represents the interaction effect. Both the regression and the ANOVA tests may include the interaction effect. The interaction terms in the regression test represent the extra contribution from the combined effects of the related predictors. They may not be used alone to answer the research question. On the other hand, the interaction terms in the ANOVA test shows the combined effects of all interaction levels. We may use the interaction plot to further explore the ANOVA results.